All right, on this problem, we're going to work another titration. Now, this is going to take several pages of work, and it may take a whole lot of time. So, if I'm limited on the videos, so I may have to split this into two, but this will definitely be part one. All right, so when we do a titration, the first thing we need to start with is we need to figure out what the equivalence point is. Now, this is when the moles of acid equal the moles of base. So the easiest way to do this is making sure it's 1-to-1 is the volume of acid, so 42.0 milliliters of acid times its concentration, 0.360 molar, is going to be equal to the number of millimolars. Okay? So when we do that, it's going to come out to be 15.12 millimoles of acid. Millimoles of acid. So that means at the equivalence point, then we have 15.2 millimoles, 12 millimoles of base at it using its concentration, so 0.240 millimoles per 1 milliliter. So we know our equivalence point is going to be 63 milliliters of base added. Okay, so what we've done at this point is we've determined the equivalence point, we've determined the millimoles of acid, and the last thing that I like to do is figure out the pKa. Remember, the pKa is minus the log of the Ka. So if we take the Ka, which is our 1.2 times 10 to the minus 2, and we take the negative log of it, then we find out that the pKa is equal to 1.9208. Okay? So, we're going to use these units as we walk through it. Now, I'm going to have to go to the next page, which is page 2. So, point 1 is when we've added 0 milliliters of base. So, it is a Ka problem. Okay, so we're dealing with our acid, which was dihydroxytartaric acid, and nobody wants to write that out. So I'm going to call this HDHT. Now, just to make sure that everybody knows, I'm going to call this HDHT. All right, so here we go. We know it's a weak acid, so it's going to go H plus DHT minus. So a simple ICE table. So our initial concentration is 0.3600 minus X plus X plus X, 0.36 minus X, X, and X. So our Ka is going to be equal to H plus times DHT minus divided by HDHT, which is going to be equal to my Ka value, which is 1.20 times 10 to the minus 2 is equal to x squared over 0.36 minus x. All right, we'll do the whole full thing, and we'll end up with x squared plus 1.20 times 10 to the minus 2x minus 0.00432 is equal to 0. We'll set it up into the poly function, and x comes out equal to 0.060 molar. Now remember, this is the H plus concentration. So we take the negative log of the H plus, which will give us 1.2218 pH. So our force point is 0 milliliters of base. And I'm going to write that below. And it's sodium hydroxide. And our pH is 1.22 for point number 1. All right, for point number 2, that's going to be the midpoint of the buffer zone. So using our Henderson Hasselbalch equation, pH is equal to pKa plus the log of our base form, which is DHT minus over HDHT. That is an H, not an A. And at the midpoint, by definition, the conjugate, DHT minus, has to equal the acid. So that means that the log is 1, which is equal to 0. So your pH is equal to your pKa, which we determined was 1.9208 plus 0. So that's our pH. Our volume of base is going to be equal halfway to the equivalence point. So our equivalence point was 63 milliliters. So halfway is 31.5 milliliters. So when we work this problem, we now have a volume of 31.5 milliliters. There's our sodium hydroxide. And our pH is 1.92. So that's our point 2. Okay? So the third one is where it gets a little tricky, is the point number 3 is at the equivalence point. That is when it is a salt. So what we have to do is set up our problem, and again it's an equation. So it's DHT plus minus plus water, because remember it's the conjugate base. It's going to be HDHT plus OH minus. Okay, so we're going to have an ICE table. So the question is what is the concentration of our conjugate base? Well, we know because we're at the end point that we're at 15.12 millimoles of the base. But our new volume is the start is going to be equal to what we started with, which was 42 milliliters, plus our equivalence point, which was 63 milliliters. So our new volume is 105 milliliters, which means our new concentration is 0.144 molar. All right, I'm going to erase that because that's not 0.144 molar. Okay, so we come back over here, 0.144, 0 minus x, 0.144 minus x, plus x, plus x, x, and x. All right, now the other trick is we need our KB. KB is equal to KW times the KA. Remember, our KW is 10 to the minus 14th. Our Ka is 1.20 times 10 to the minus 2. That's actually a pretty strong weak acid, so our Kb is going to be really low, which is 8.333 repeating times 10 to the minus 13. So that's pretty weak, actually. So our Kb is going to be equal to the HDHT times the hydroxide divided by DHT, and which is equal to X times X over 0.144 minus X is equal to 8.3333 times 10 to the minus 13th. So when we work this, we end up with X squared plus 8.3333 times 10 to the minus 13th X minus 1.2 times 10 to the minus 13th, which is 0. We're going to plug it through our poly function. We find out that X is equal to 3.4641 times 10 to the minus 7th, which, remember, that's the hydroxide ion concentration. So my pOH is equal to 6.4604, which makes my pH equal to 7.53. Because remember, pH plus pOH is equal to 14. Alright, so my point number 3, we're going to be at 63 milliliters of sodium hydroxide. And our pH is now a whopping 7.53. Okay, that's the 3 points. The 4th point is relatively simple. So the 4th point is basically a strong base. Now, there are 2 ways to do this. You can pick a point. So you pick a point greater than 20 mils past the equivalence point, or you can keep it simple. The most it will be will ever be pH wise is the pH of the base. So your base was 0.240 molar. Now remember, it's never going to get there, but it's going to approach it. So if you take the negative log of 0.240 molar, that gives you a pH of a pOH equal to 13.38. Excuse me, that was my pOH. My pH. So my pOH is 0.6198, which means my pH is equal to 13.38. Okay, so this last point is infinity, because you're going as most as you can, sodium hydroxide, and your pH is 13.38. So if we go back to our original graph, then it's asking us to graph the points. So here is my pH. Here are my milliliters of base added. Now, you want to make it as big as possible. Sometimes that doesn't work. We know our endpoint is 63. So if we look at it, 5 is going to be the best. That's 10, 20, 30, 40, 50, 60, 70, 80, 90, etc. And you can go up to 100 if you want. Okay, and our pH, remember I give you the units 2, 3, 4, 6, 8, 10, 12, and 14. So our first point, remember, is going to be 0, milliliters, and it's going to be 1.2. So this is very hard to do on this side. So I ask that you put the points in: 0 milliliters, 1.22 pH. My second point is 31.5 and a pH of 1.92, so that's 31 and 1.92, so that's approximately here. Again, 31.5 milliliters with a pH of 1.92. Our second point, or excuse me, our third point is the 63, which goes here plus, and it goes to 7.5. So it's somewhere around in here. And again, this is very hard to do on this air sketch. Let's try this again. 63, 7.5, somewhere around here. Again, that's why I have you write the point: 63 milliliters, 7.53 pH. And then our last point, we're going to go to infinity, and it's going to max out as 13.38. So this is infinity milliliters and 13.38 pH. So when we go to graph it, what you're going to do is go up and kind of level off, and then go straight up, and then level off there. So now we have graphed it. Now, the last point we didn't do was the buffer point. So for a buffer, we're given 48.5 milliliters of sodium hydroxide. Now, when we look at that, what that means is that we have added 11.64 millimoles of base. And remember, we got that by multiplying it by our concentration, which was 48.5 milliliters times 0.24 molar. Okay, that gives me millimoles of base. So what we've done is the hydroxide, which is the base, is added to the HDHT to produce the weak conjugate base plus water. So we originally started with 15.12 millimoles here, and we added 11.64, and so initially we had 0. So we're going to lose all of our base because we're going to convert it all to the weak. So when we're done, we're going to have 3.48 millimoles of the weak acid, and we're going to have 11.64 millimoles of the conjugate base. So where pH is equal to the pKa, because this is a buffer, times the conjugate, which is DHT minus, over HDHT. So pH is equal to 1.9208 plus the log of 11.64 over 3.48. So that's equal to 1.9208 plus the log of 3.3448, which is 1.9208 plus 0.5244. So in the end, my pH is equal to 2.4452, which is 2.45 at this buffer point. So at this point in time, we have worked the problem.